So this question starts off quite straightforwardly. It's about you remembering the expression for Kw, and the correct answer that we're looking for is C. H plus times OH minus, obviously concentration in moles per decimeter cubed, so it's square brackets. It's worth pointing out at this point that if we were doing this as a Kc expression for dissociation of water, it would be H plus times OH minus over H2O. But because so little of the water dissociates, we can actually assume that the water concentration remains constant, and that's how we're able to leave it out on this one. So we take a look at this first calculation here. We know, as I've said, that the pH of pure water is 7, but actually that's only true at 298 K, and this is at a lower temperature. Now, to begin with, what we're going to do, I've started by writing the Kw expression, H plus times OH minus again, and I'm reminding myself that when water dissociates, each H2O will yield an H plus and an OH minus. So for that reason, I'm going to assume that my H plus concentration is equal to my OH minus concentration. Now that means I can simplify my Kw expression. Rather than H plus times OH minus, if they're the same, I can say that Kw is equal to the concentration of H plus squared. And if I then rearrange that again, because I want H plus, not H plus squared, we can see that that's equal to the root of Kw. Now, we were given the Kw value at the start of this question, so I find the square root of that. That gives me my H plus concentration, which I can then put into my pH expression, giving me a pH of 7.27. Now, always on a calculation, ask yourself, is that reasonable? We know that it's 7.00 at 298 K, so a number relatively close to 7 does seem reasonable. So then I would be happy to move on. But then we have this question about why it's not alkaline, because certainly lower down prior to GCSE, anything above 7 would be classed as alkaline. But we're actually going back to one of the pieces of information that we used to get to this answer. There is no excess of OH minus. So it can't be alkaline. It remains neutral because I don't have the H plus or OH minus in excess. If I move on to 3.4, calculating the pH of a base, a strong base. Now this utilises the Kw expression, but in a different way. So from this, I've got to remember quite a number of things actually. I need to work out my OH minus concentration. To do that, I've got to realise that calcium hydroxide has the formula CaOH2. And to do that, I've got to remember that calcium has a +2 charge and hydroxide ion has a -1 charge. But if I do that and I work out my 0.0262, I've got my 1 mark, my first of 3. I'm then going to take my Kw expression, and this time, because I want to know what the pH is, I'm going to rearrange it to make H plus the subject. I'm not assuming H plus and OH minus are the same here because we're not dealing with a neutral solution. Once I put those figures in, and I've got my Kw expression once again from right back at the beginning of the question, divided by the concentration of OH minus ions, that then gives me my concentration of H plus. That's going to get me my second mark, so that's 1.118 by 10 to the -13 mole dm to the -3. I then put that number into my pH expression, and I get to a pH of 12.95. I've satisfied the criteria of the question. I've done it to 2 decimal places. And again, I'm going to ask myself, is it reasonable? And if I'm dealing with a strong base, a pH way above 7, somewhere close to pH 14, does seem reasonable to me. So I would be confident at that point that I could move on. We then move on once again. We've got another acid-base themed question, so there's quite a lot that's being thrown at you here. And we want to know what the pH of magnesium hydroxide would be compared to calcium hydroxide. Now the pH is going to be lower. It's going to be closer to 7. And the reason for that is that magnesium hydroxide is a weaker base than calcium hydroxide. This is actually taking us back to work that you have done on group 2. So moving to a different topic. But we know that magnesium hydroxide is less soluble because we know the trend in solubility of group 2 hydroxides is that they get more soluble as you descend the group. So we're jumping from a very calculation heavy acid-base question to a different topic area within the same question.